Hello everyone and welcome to the last section of section 8.4, so calculations involving acidic solutions. So there's been quite a few calculations here, so we're going to take a little break from calculations here just for a couple minutes to talk about something called polyprotic acids. Right, so the acids that we've kind of seen so far, a lot of our strong acids, so just like your HCl, your HNO3, HClO4, right? These all have, if you look at them, right, they have one hydrogen that's able to be donated, right? So these acids, right, are actually not called polyprotic acids. They are called monoprotic acids. Right? So meaning that they have one proton that they're able to donate to another entity, whether that's water, whether that's a base or a base of any kind. They're monoproducts, so they can only donate up to one of those H plus ions. However, there are other things, so you've probably heard of sulfuric acid, right, which is H2SO4. With this H2SO4, you're going to notice that there are two hydrogens that they will be able to donate. And with these hydrogens, what they can do is they can actually exhibit a multi-step reaction. So with H2SO4, sulfuric acid, right, there are two steps that it can undergo in order to act as an acid. So first off, it can go H2SO4, say we add it to some water, right, and it will end up reacting to produce H plus and HSO4 minus. Now you'll notice here I put an arrow that was not showing that it was at equilibrium, right? For most polyprotic acids, their very first reaction basically occurs 100% in the rightwards direction, resulting in H plus ions and HSO4 minus ions, right? The second reaction, however, HSO4 minus, reacting to produce H plus and SO4 2 minus, occurs at equilibrium. This is because the Ka value, right, of this one is going to be quite high, or significantly higher than this one. Right, so let's just put an arrow for high. Right. However, the second reaction, and with all polyprotic ions, the Ka of the second reaction is going to be relatively low. Right. So the hydrogen, what this means is that these hydrogen or these H plus ions that are produced are not going to be produced very readily. So they may produce a few. However, it's not going to really produce a significant amount of H plus ions in order to contribute to, say, decreasing your pH or anything like that, right? So it's interesting because we can actually exhibit these two Ka values using different ionization reactions. So our first one, we always indicate these as Ka1. Right? So that would be for this first reaction here. It is going to end up equaling, just like we have before, the concentration of H plus times the concentration of HSO4 minus, all divided by your concentration of H2SO4. So nothing's different. Right? And your Ka2, I'll do that in a different color, your Ka2, exact same thing, we're just now using this reaction right here. So it's going to equal the concentration of H plus times the concentration of SO4, 2 minus, all divided by the concentration of HSO4 minus. Right? This value right here is going to be significantly different than the value that you are going to see up here. This one's going to be big. This one's going to be rather small. However, we need to understand how these things work in order to do some calculations moving forward. All right. So what we can see is I'll just throw out a couple different Ka1 values. So let's look at oxalic acid. All right. For Ka1, oxalic acid, right, has a Ka1 of 5.4 times 10 to the negative 2. So 10 to the negative 2, 10 to the negative 2, that's a pretty big number in terms of K values, right? Whereas Ka2 is 5.4 times 10 to the negative 5, right? So that's getting a little bit smaller. So that's going to produce far less hydrogen ions than the Ka1. All right, we'll look at one more. Let's look at sulfuric acid. So from our demonstration before, acid. Right? The Ka1 of sulfuric acid they don't even have a number for it. It is just very large. And the Ka2 for that is 1.0 times 10 to the negative 2. Right? So we're seeing that there's quite a common trend with your Ka1 being significantly larger than our Ka2. And we're able to use this, especially when we're calculating pH or things like that. So the ion concentration that is going to be produced from our secondary reaction, so this one, say, right up here, is going to be rather insignificant. Right? However, we're going to look at it anyways, just to go a little bit more in depth on it. However, the majority of our H plus ions that are going to contribute to, say, pH are going to come from our Ka1 reaction. So we'll get into just a quick little, the last sample problem that we're going to go through for this section of our notes. Is calculating the pH of a polyprotic ion or a polyprotic acid solution, which is ascorbic acid, all right, which has a formula of H2C6H6O6, and it's in a 0.10 mole per liter solution, right? And we are asked to calculate pH, right? So I'm going to show you how we can calculate the pH quickly. But then we'll just do a little bit more of an investigation to see really why this Ka2 reaction really isn't going to contribute much to that overall pH. So starting off with this, right, we need to compare, right, our Ka1, our Ka2, and our Kw to make sure that we know exactly where the majority of our H plus ions are going to come from. So if I look here, my Ka1 is going to be 7.9 times 10 to the negative 5. My Ka2 is 1.6 times 10 to the negative 12. And finally, my Kw, as we know from before, is going to equal 1.0 times 10 to the negative 14. So as we can see here, these two K values are very small. So we can tell just by looking at these three values that the majority of our H plus ions are going to come from our Ka1 reaction. So this is what we're going to focus on first, right? This is an important step because sometimes they might throw a curveball at you and it may not be the reaction in question. So we have to make sure that we know how to analyze these things if we're not necessarily given things to line up exactly how we would like them to. So our first step that we're going to do is we're going to write down our Ka1 equation. So before we do that, let's just write down a quick balanced equation in order to show how this reaction is going to proceed forward. So we're going to have our H2C6H6O6, and it is going to react in equilibrium to produce H plus ions, right, as well as HC6H6O6. So we're just seeing that this proton here is being donated, whereas we're only left with one proton, or this would be a monoprotic acid, right, for the next step if we chose to go that way. So based off of that, what we can do is we can make our Ka equation. So if we write Ka1 is going to equal the concentration of H plus ions times the concentration of HC6, right? So from over here, H6O6, all divided by our concentration of our original acid, which is H2C6H6O6. And once we do that, then we can initially just start solving for X. However, it's always helpful just to quickly throw it into an ICE table just to make sure that we know exactly what's going to happen to our concentrations at equilibrium. So let's do a quick ICE table here. So we're going to do I, C, E, right? We are going to have our H2C6H6O6, our H plus ions, and our HC6H6O6. All right, and using that, we can show our initial concentration. So if we look up to the start of the question, we can see our initial concentration of our acid is going to be 0.10 moles per liter. So I can write in here 0.10 moles per liter. Obviously, we're going to start with 0 moles per liter for H plus, and we're going to start with 0 moles per liter for HC6H6O6. All right. Our change, again, as we've always seen in most of these reactions, this is a 1 to 1 to 1. All right. So that means that all we have to deal with is a single X. We don't have to input any other numbers for that. So we're going to see a negative X here, a positive X for our H plus ions, and a positive X for our monoprotic acid. So again, we are going to see our equilibrium concentration, 0.10 minus X. This will just end up as X, and this one will end up as X as well. All right. So once we have that, right, we can start subbing this stuff into our Ka equation in order to solve for that X value, right? So again, Ka1, actually, you know what? I'm just going to scrap rewriting that. It's just up here. So I'm going to take my Ka1 that was given to me at the start of the question right here. So I'm just going to write 7.9 times 10 to the negative 5. And that is going to equal the concentration of H plus ions. We don't necessarily know what that is yet, so we're just going to put in our X from right here, our equilibrium concentration. We're going to put in another X, all right, for our HC6H6O6 because of our equilibrium concentration from our ICE table. And we're going to divide by 1.0 or 0.1 minus X. All right. As soon as we see this, we think, oh no, we don't want quadratic equation. So let's try and do everything in our power to get rid of this X at the bottom. So then that way we only have to deal with 1 squared X, and we can just simply square root everything. So to do that, again, we need to do our rule of 100 or 100 rule. Therefore, we need to check our initial concentration of our H2C6H6O6 and divide that by our Ka1. All right, so that's going to equal 0.1 moles per liter divided by our Ka1, which is 7.9 times 10 to the negative 5. And we're going to see that that ends up giving us If I just quickly pull up my calculator, 0.1 divided by 7.9 times 10 to the negative 5, that's going to give us 1.26 times 10 to the 3. So 1.26 times 10 to the 3, obviously much larger than 100. So our assumption is that 0.1 minus x, right, is still going to be approximately equal to 0.1 moles per liter. All right, and we'll check this assumption later, but for right now, we are going to use it moving forward. So we can essentially move up to our Ka1 equation, right, and we can kind of get rid of this x. So I'm just going to flip over to the next page. So I'm just going to quickly now sub everything back in for my Ka1 equation. So let's do this one in blue. 7.9 times 10 to the negative 5 is going to be equal to concentration of x. I'll write it out all the way for right now. All over 0.10 moles per liter. All right. This is obviously going to condense as these multiply together into x squared, so it will look like this. All over 0.10 moles per liter. All right, so I'm just going to now multiply both sides by 0.10 moles per liter. All right, and we will see that if I'm multiplying by something in the denominator, I can actually just cross those out because they are going to cancel each other out. And I'm just going to be left with 0.10 moles per liter times 7.9 times 10 to the negative 5 is going to be equal to x squared. Right? So when I do that, if I multiply this by 0.1, all it's going to do is just add another negative exponent there. So that will just end up being 7.9 times 10 to the negative 6 equals concentration of x squared. Just like we've done in all of our other examples, square root both sides so that we can get x on its own. So the square root is going to cancel with that square, leaving us with just x. So our square root of 7.9 times 10 to the negative 6 is going to equal x. So I can quickly do that on my calculator. I'm just going to take here 7.9 times 10 to the negative 6. And then I will square root that value, giving me 2.81 times 10 to the negative 3. So 2.81 times 10 to the negative 3 is going to equal my x value. Now this is important because if we look back to our ICE table that we created, that x value down here is going to equal our equilibrium concentration for both H plus and HC6H6O6. All right. So now what we can do is we can just simply use our pH calculation that we've used so many times before in order to solve for the pH of this reaction. All right. So I'm just going to take my pH equation, which is pH equals the negative log of the concentration of H plus ions in solution, right? I know from my ICE table, right, which is right here again, right, that our ICE table, this one, my ICE table here, X is going to equal H plus, right? So I can simply just put in this value here for my concentration of H plus ions. So pH is going to equal the negative log of 2.81 times 10 to the negative 3 moles per liter. Right? So luckily I still have it on my calculator. So I'm just going to click negative log And then I'm just going to input my answer here, which is my 2.81 times 10 to the negative 3. And if I click equals, it's going to give me 2.55. So that means the pH of this solution is going to equal 2.55, right? So theoretically at this point, we've solved the answer, all right? We've found the pH of the solution, but I just want to show you very quickly how the second reaction does have an effect. However, it really doesn't affect the pH overall. So what we'll do is very, very quickly, I'll just pull up another page here. We can actually go forward in order to calculate, and you might be asked at one point, maybe calculate the equilibrium concentration of your ascorbic acid. Or you may be asked what's going to be the equilibrium concentration of your, where is it here? The equilibrium concentration of potentially your last acid from your second reaction, which would just be your C6H6O6 2 minus. All right, so you may be asked these questions, so I still want to go through this, even though we really have already answered the question. So what we would need to do in order to determine, say, the equilibrium concentration of our C6H6O6 2 minus. Say if we want to solve for that, right? The very first thing that we need to do is throw everything into our Ka1 equation in order to solve and determine the concentration, or first the equilibrium concentrations of our HC6H6O6, which was the monoprotic acid that was produced at the end of the last equilibrium reaction. So to do that, I'm going to already know that my concentration of my H2C6H6O6 from earlier is just going to equal 0.10 moles per liter minus X. Right? So I'm going to take that, I'm just going to put 0.10 moles per liter, right? And I'm going to subtract, I believe it was 2.81 times 10 to the negative 3, right? What that's going to give me, so it's going to be very, very close. So as you can see, 9.72 times 10 to the negative 2. So it's essentially going to be very equal to this 0.1. However, we'll write that out. So it's going to be 9.72 times 10 to the negative 2. And that's going to be our concentration of H2C6H6O6 at equilibrium. Right, so as you can see, it really didn't lose much of its concentration whatsoever. Right? Now, with using that value, what we can actually do now is put it back into our Ka equation in order to solve for so sorry, I kind of got mixed up here. So I was actually trying to solve for our HC6H6O6, right? So its final concentration in order to give us the initial concentration for our next equilibrium reaction. So that was my bad there. So just kind of scratch all this stuff here. Don't worry about paying attention to that. So as you know, your concentration, your equilibrium concentration is just going to be equal to X. So our initial concentration for our second Ka2 reaction of HC6H6O6 is going to equal just our 2.81 times 10 to the negative 3. Okay. So say we're looking for our final equilibrium concentration of this here reaction. So what we can see is that the reaction will happen where HC6H6O6 is going to react in equilibrium in order to produce H plus ions and C6H6O6 minus 2 minus ions. All right. So here we can just make our Ka2 equation, which will be the concentration of H plus ions, the concentration of C6H6O6, 2 minus ions, all divided by the concentration of HC6H6O6. All right. If we were to create a really quick little ice table here, so I'm not even going to, I'm just going to label these 1, 2, and 3. So if I make an ice table here, and I have 1, 2, and 3, my initial concentration for this is going to be 2.81 times 10 to the negative 3. My H plus is going to be starting at its initial its final concentration, which will also be it'll be negative 2.81 times 10 to the negative 3. And finally, your C6H6O6 2 minus is going to start at 0. Right? So what you're going to realize is this is going to decrease by x, right? This one here is still going to increase by x, right? And this one here is going to increase by x as well. So we're still going to be left with 2.81 plus x, and this one's going to be just x, and this one's going to be minus, or 2.81 minus x, right? So we can see here, with the Ka2 being so small, this value here is going to be approximately equal to 2.81. So we're not going to see really any change in the pH of the concentration. However, we can still go through in order to find our values for our concentration of C6H6O6 2 minus. So if we do that, our Ka2, if we put it in here again, right, if we're solving for this here, right, and we make the assumption that our H plus here, because the Ka2 value is going to be so small, it is 1.6 times 10 to the negative 12. Right, we're going to assume that our H plus is just going to stay at 2.81 times 10 to the negative 3 multiplied by some concentration of C6H6O6 2 minus, all divided by our concentration of HC6H6O6, which we can also determine is probably not going to change because it is going to be such a small Ka2. So we're just going to write that as 2.81 times 10 to the negative 3. All right, so you'll see here that very quickly things are going to start canceling out. And what you're going to be left off with is that if we cancel this and this, essentially our 1.6 times 10 to the negative 12 is going to equal our concentration of C6H6O6. All right. So with that being said, you're going to notice a lot of these trends are going to stay true through each one of these types of reactions. So what I want you to try and do here now, just for practice for the rest of class, there's going to be no more videos today. You're going to just complete practice questions 1 and 2 on page 524. All right. And if you're able to get that done before the end of class, there are some good questions on page 525. I will let you look through those ones. I'm not going to tell you specific ones. Most of them have multiple A, B, C, D, all of those things. So just go through each one and maybe just try an A or a B from some of them. Don't do all of them. However, with these types of questions, there's a lot of benefit in practicing them over and over and over again, because we're going to see that there are just going to be some slightly different types of reactions in each one of these questions. So it's good to be familiar with a bunch of different variations of these types of questions. But with that being said, I will let you go. Hopefully everybody has a great weekend, and I should see you all back on Monday. So good luck in the rest of your practice today. And if you have any questions, feel free to email me at any time. Thanks, and have a good weekend.